Well, hello, chickadees. I don't know why I start off every video so weirdly. I could just start off by saying, hi, kids. It's a great day to see you. It's Unit 9.6 notes. It's a work day. No, that's no fun. Ooh. Still good, but cold. Anyway, let's get going. This is day 6. What we're going to be doing today is a whole bunch of practice. So, practice. Let's talk a little bit about practice. By the way, hopefully at some point all of these videos will be up at www.nkinfinity.com. Me and my partner, Miss Vicki Newman. I'm Mr. Key, otherwise known as Mr. Krause, for today. Practice. Let's talk about practice. Do you think people get better practicing watching other people practice? Like if I go to a basketball practice and watch a basketball practice, would I get better at basketball? If I went to a soccer practice and I watched kids dribble and juggle and shoot, would I get any better at dribbling, passing, and shooting? How about if I watched a football practice and I saw kids hit and run and throw and do all that stuff? Would I get any better? No! No! So don't sit here and watch me. I'm ugly. You don't want to watch me this whole time anyway. You got to practice these problems on your own. There are 10 questions right here at the beginning. Try these. My dogs, I go like this and they go crazy. Try these on your own. See what you can do on your own. Then come back and see if you can figure things out. All right? There's my lecture. So try these first 10. Fly through. See if you know how to do them. If you don't know how to do them, come back. Check with me. Where do we find the joint frequencies? Like if we're looking at a frequency table, where are the joint frequencies? They're inside the table. Where are the marginal frequencies? They're on the margins. On the margins. I know that sounds stupid, but on the bottom and the right side. Those are the marginal frequencies. Oh, I forgot I was going to work on my neatness. On the right side, those are the marginal frequency. What is the difference between a frequency table and a relative frequency table? All right, so a frequency table, the numbers in the table are the probabilities. Well, in a frequency table, we know the actual numbers, but in a relative frequency table, we only have the percentages. So we really can't tell, unless we are told there were 10,000 people that were surveyed, we only have the percentages. They're going to add up to 100%, of course, but is that 100% of 10 people that were asked or 100,000 people that were asked? So unless we're told that, we only have those percentages. So relative frequency has percentages in there. Frequency table has the numbers, actual numbers in there. What is the formula for conditional or, in quotes, or probability? I should say, in quotes, or probability. Okay, so that's the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Get used to it, kids. Use the notation for the statement, the probability of A given B. So we want you to write this. The probability of A given B. Oh, not G. Remember that line stands for given. And of course I can do it the other way around, the probability of B given A. If A and B are independent, then the probability of A given B is just equal to the probability of A. That's one of our rules or tests for independence. If A and B are independent, my other rule is that the probability of A and B is equal to the probability of A times the probability of B. If A and B are not independent, then we have to use the other form, and we can use this is equal to the probability of A times the probability of B given A, or we can use the probability of B times the probability of A given B. Either one of those would be acceptable to prove or to show independence. Oh, here we go. What are the two ways to show independence? We show that the probability of A is equal to the probability of A given B. Or probability of B is equal to the probability of probability of B is equal to the probability of B given A. In other words, knowing that A occurred had no effect on what B's probability is. Or we can show that the probability of A and B is equal to the probability of A times the probability of B. So though this information, all of this information should be in your wheelhouse. You should just know it. It should be stuff you just committed to memory. You understand it. You understand the principle behind it. Otherwise, you need to go back and go review the videos. Go back and see your teacher. Come back and see me. Whatever it is you need to do. You need to make sure this stuff's all in your wheelhouse, that you understand what's going on. All right? When I unpause this, I will come back and we'll do some practice problems. All right, kids. Again, now you should not be watching the monkey perform. Okay? Watching me practice is not going to get you to the point where you need to be. And you could say, but I don't get this stuff. I don't understand this stuff. I get it. But you have some formulas. You got to try something. Got to try something. Okay? You want to do one problem at a time? That's fine. You want to go do 5 problems at a time? Go do 5 problems? That's fine as well. Whatever you need, okay? All right. What is the probability A and B if A and B are independent? Now, because I gave you independence, that tells you that the probability of A and B is equal to the probability of A times the probability of B. That's what it gives you. Remember, we got up here, excuse me, up here is our test for independence. If this is a test for independence, and then they tell us that they're independent, then we can use that information. Well, why do I need that? Well, I need that because I know that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of their combined or their overlapping part, which is probability of A and B. But again, we're going to replace this with the probability of A times the probability of B. So now I'm ready to rock and roll. 0.25 plus 0.34 minus 0.25 times 0.34. And if I do that, I end up with, I believe, 0.505, but I'm going to check my work. Got to check your work. So what is it? 0.34? 0.25 times 0.34. Nope. 0.25 plus 0.34 minus 0.25 times 0.34. 0.505. There we go. All right. That's problem over with. It wasn't bad. One quick formula and a substitution that we had to make in that formula based on some given information. All right. So in doing research, they recommend that you check more than one site. The probability the answer can be found on Google is 9.95. On Bing is 0.92. And on both sites is 0.874. Are the probabilities of finding the two answers on the websites independent? How do you know? So it's not good enough just to say yes or no. That's not good enough. That won't give you any credit at all. You have to prove yes or no. So if in fact they are independent, that would be the probability of Google and Bing is equal to the probability of Google times the probability of Bing. Well, what is the probability on both? On both means probability of Google and Bing is correct. Well, we know that to be 0.874. Well, let's do the probability of Google is 0.95. The probability of Bing is 0.92. So I need to show, oops, not probability. The probability of Bing is 0.92. I need to show, do those two multiply to give me 0.874, or do they not multiply to give me 0.874? So 0.95 times 0.92, 0.874. So because 0.874 equals 0.874, the probabilities of finding the answer on Google and Bing are independent of each other. Because, and we just proved it over there, because the probability of A given B, A and B is this equal to the probability of A times the probability, or in this case, the probability of Google times the probability of Bing. All right, before we get started on this one, let's pause. Nothing like good old crazy politics to get things all worked up. When I'm about to delve into some crazy politics that makes half the population crazy mad and the other half of the population crazier mad, I drink some Dunkin' Donuts coffee. It calms me down just a little bit. All right, kids. I hope that you already have taken the time to figure out what these numbers are. This one I came up with was 1573, and this one over here 4510, and this one is 459, and this one is 310, and this one over here is 4750, and it looks like, doesn't even tell us, but it looks like we've interviewed 25,000 people. I hope those numbers add up to 25,000. All right. So we've got event A, vote for Clinton. Event B, vote for Trump. Event C, vote for somebody else. We've also got our, we strayed it into our demographics too by age. Okay. We could have done female and male too, but you can do this all day long. So, what is the probability of A, voted for Clinton? Well, we know the denominator is 25,000. Who voted for Clinton? 11,860. Now, remember, this is just this particular survey. We know that Clinton won the popular vote, but remember, this is only a survey of 25,000 people. Some 60 million people voted. All right, what's the probability of G? G is 65 years or older. That's over here. 4750 over 25,000. So far, so good. What is the probability of A and F? Let me get rid of some of my drawings I've written already. A and F. So let me do A. A is voted for Clinton. And F is 44 to 64. So A and F, we're looking for where they cross. Where do they hit each other? And that is at this space right here. So it's 4510 over 25,000. Yep. All right, let me get rid of that because I know I'm going to need some other stuff. Probability of C and E. Let's do C, which is voted for another. So that's this. And E, which is 29 to 44. So in other words, we've got 459 people that chose not to say or chose not to vote for one of the two Democrat or Republicans, but they just in the age group of 29 to 44. So 459 out of 25,000 people. All right, what else we got? What is the probability of B given G? So this is so given that we're in G, okay, remember what this means, right? Given G, this is now my new universe. I can only think about G. Whatever G is, I can only think about G. So the only thing I can think about is right now are people that are 65 years or older. I can't think of any of this other stuff. I don't care about any of this. I don't care about this. I don't care about this. The only thing I care about is that yellow line right there. So what is the probability that B voted for Clinton given that they're older than 65? B given G. And they voted for, what is the probability of B voted for Trump given that they were older than 65? And that would be this number, voted for Trump given that we're in this one. So that would be 2518 over 4750. All right, so let me get rid of all that crap. Wouldn't you wish you could erase like this? You could if you got a tablet. All right, so what are we going to do now? I want to know what is the probability. Okay, now we voted for Clinton, so we have a vote for Clinton. That's my new universe, is voting for Clinton. And then, so my new universe is here. That's the only thing I can think about. All of this stuff, gone. Can't think about it. So what is the probability that that I'm 18 to 29 and I voted for Clinton? There it is, 238 out of 11,860. So not 238, 2,338 out of the 11,860. All right, C or E. Now remember, this one's a little bit tricky. This is the probability of C plus the probability of E minus their overlap, the probability of C and E, right? And I think it's really easy to do this on these frequency tables because you see the overlap. So here, let me do this one. Probability of C or E. Now, C is voted for somebody else. So we're going to go down this aisle. And E is 29 to 44. Where do they overlap? Oh, there's the overlap. So the probability of C is 1203 out of 25,000. The probability of E is 5,748 out of 25,000. But we've counted this 459 twice. We got to get rid of that. So we're going to come back down here. Then we're going to say this is equal to 1203 over 25,000. I got to write it small. I didn't give you much room here. Plus 5748 over 25,000 minus that 459 that repeated itself. We did that. We counted it twice. And if I did that correctly, I should end up with 7,410 over 25,000. All right, probability of Bud, B or D. So this would be the probability of B plus the probability of D minus the probability of B and D. Counted it twice. So probability of B is Trump. Probability voted for Trump. D is 18 to 29. So what did I count twice? I counted this twice. So these are Trump. out of 25,000. These are all the young kids, 18 to 29, and all of it's out of a total. So come down here, and I'm going to do this again. We're going to take voted for Trump, 11,937 over 25,000. By the way, these numbers are just made up. Don't read into this. I love doing controversial politics and mathematics. You know why? It makes you awake. You know, half you like, going, I can't believe he won. The other half like, ooh, I can't believe he won. Whatever your politics are, I don't really care. I do like having you a little bit angry while you're doing a little bit of math. And what do we come up with? 14,613 over 25,000. All right. Are A and G independent? All right, so in other words, is the probability of A equal to the probability of A given G? Well, the probability of A, that's Clinton, is 11,860 over 25,000. Now, G is... Did I do a probability of, I didn't do, do I do a probability of A given G? I didn't. That would have been nice. So what is the probability of A given G? So given G, so G is my new universe. That means I've got, this is my new universe, G. How many people voted for Clinton in my new universe? 2137 over 4750. Over 4750, I believe. 11,860 over. So that, you know, nobody, I can't in my right mind tell you if those are equal or not until I turn them to decimals. So I certainly got to turn them to decimals. 11 divided by 25,000. 0.4744. So 0.4744. Does that equal 2137 divided by 4750? 0.4499. Since these are not the same, A and G are not independent. You'd have to answer that. Are B and E independent? Well, again, on this one, we're going to have to prove that the probability of B is equal to the probability of B, given that E has already occurred. So E is my new universe. First of all, probability of B, which is, B is Trump. So the probability of Trump is pretty easy. 11,937 over 25,000. And just so you know, that is 0.4774. 0.4774. Wow, that was pretty close to what I put up for Clinton. That's weird. And let's do B and E. So my new universe is E, which is 29 to 44. Wait, did I do B and E already? That would have been nice. My new universe is E, which is 29 to 44. So it's only these people, 57. So it's 2414 out of 5748. 2414 out of 5748. And this is equal to 0.41997. And once again, they are not independent because they are not equal. All right, kids. And in any cases, they'd almost never be independent there. All right. I will pause and be right back. I love fooling you all. Okay, let's get off of politics. All right, so we got some more math problems to do. Now we're going to just, I don't know if there's any more tables. Maybe I got one more table. I got a lot of problems to do. All right, suppose that P of K equals 0.25 and P of L equals 0.4 and P of K equals P of L. What is P of L given K? What? Say what? So notice these match, right? Check this out. Notice this matches this. That leads me to believe I'm going to use the probability of L and K is equal to the probability of L times the probability of K given L. Now I have to use this one and not the other one because I'm not certain if they are in fact independent. In fact, I know they're not independent because check this out. The probability of K does not equal the probability of K given L. So I know they're not independent. So that means I have to use this formula for not independence. Was that one up here? Which formula do you have to use if they are not independent? Right? So this is the kind of thing you got to be thinking about. Did I say independent or not independent? In this case, I said not independent, so I have to use this formula. Okay, so what is the probability of L and K? I don't know, but I know the probability of L is 0.40, and I know the probability of K given L is 0.20. That means the probability of L and K equals 0.80. Or 0.08, excuse me, 0.08. All right, well, how does that help me out? Well, that helps me out tremendously. I'm just going to use that same formula, the probability of L and K, but this time I'm going to use the probability of K times the probability of L given K, which is the thing I'm actually looking for. Okay, so I know that now we know that this is 0.08. We also know that the probability of K is 0.25. Now I can use that to find the probability of L given K. Divide by 0.25, and I get what, I don't know. I always do that. Wait. Oh, still recording. Hi, it's still here. Oh, it's a good thing I didn't use any F words because I was thinking about it. You know, like fraction and fun and factoring. You potty mouths. 0.08 divided by 0.25. 0.32? That's what I thought. Multiply by 4. So the answer is 0.32. And I can't find a mouse. 0.32. All right, moving on. Given that 49% of the lion population are male and 12.1% of the population of lions is over the age of 10 years in age, over the age of 10 years in age, boy, that was written by a math teacher. Can we conclude that 0.49 times 0.21 equals 5.29%? Remember, this is really 0.05929 as a decimal. Are older than 10 years, or older than 10. So what they're asking for is the probability that they're male and greater than 10 years old. Is that equal to the probability of male times the probability of greater than 10 years or age or older? Well, let's see if that math's even right. What is this math? 0.49 times 0.121. 0.50925. So can we conclude, now this is the probability of male, which is 0.49, times the probability that they're greater than 12, 0.121. Can we conclude that that's equal to 0.0529? It is equal to it. Mathematically, if I add it, there it is. There it is right there. But can we conclude that based on the population of males? And so here are my answers. Yes, by the multiplication rule. Okay, I did multiply them. I did get them. By conditional probabilities, there was no conditional probabilities in this one, so that wouldn't work. The law of large numbers has nothing to do with this one. The law of large numbers just basically means if I flip a coin and I get a heads, and then I flip a coin and get a heads, and flip a coin and get a heads, and flip a coin and get a heads, and flip a coin and get a heads, eventually I'm going to flip coins for a long enough time that I'm not going to keep getting heads, and eventually it'll be 1/2 of heads, 1/2 of tails. So that's not it. No, because the events are not independent. No, because the events are not mutually exclusive. That really has nothing to do with it. Mutually exclusive has nothing to do with this. So, well, when can I use this formula? When am I allowed to use this formula that the probability of an and is equal to the probability of, you just multiply the probabilities. And the only time I'm allowed to use that probability is if the two events are in fact independent. And I don't see anywhere in this problem where they said that they were independent. So I'm saying the answer has to be no, because they are not independent. Not only they're not independent, we weren't told they were independent. So we can't use this rule. Tricky question. Suppose that probability of W equals 0.3. The probability of W or M equals 0.7. What is the probability of M if M with W and M are mutually exclusive? Mutually exclusive mean they have zero. Mutually exclusive means the probability of the probability of W and M is equal to 0, right? Oh, God. So that's what mutually exclusive means. The probability of W, well, what does that help us out with? Well, that helps us out with this, that the probability of W or M is equal to, now this is if they are mutually exclusive, we're talking about right now, mutually exclusive, is equal to the probability of A, I keep using A, the probability of W plus the probability of M minus the probability of W and M. Well, if they're mutually exclusive, there's nothing, they have nothing in common. That's got to go away. So it's just equal to the product of these things. Well, this is 0.7 is equal to, what are we given? 0.3? 0.3 plus plus the probability of M. Well, the probability of M then, if I do a little bit of math, is equal to 0.4. So I know the answer is 0.4 for the probability. If they're mutually exclusive, the answer is 0.4. So I know it's one of those two. If they're independent, now what is my test for independence? My test for independence is, how does that work? Then that's equal to the probability of W and M is equal to the probability of, if they are mutually, or if they're independent, that's equal to the probability of W times the probability of M. Right? If they're mutually exclusive. Something's wrong with my chest. All right, my ribs right there. Okay, so I'm going to use this information then and this same formula. But in this case, the formula has to include this part now. So the probability of W or M is equal to the probability of W plus the probability of M minus the probability of W and M, but I'm going to get rid of that, and I'm going to use the probability of W times the probability of M. Now I'm going to sub in everything I know. Probability, this is 0.7, is equal to probability of W, 0.3, plus, I don't know the probability of M, so I'm going to put probability of M, minus the probability of W is 0.3 times the probability of M. So we've done a problem already similar to this. Let me solve this. I'm going to bring the 0.3 over, so I end up getting 0.4 is equal to, so I brought this over to the other side. Now this is This is the part that's a little bit tricky. This is 1 probability of m minus 0.3 probabilities of m. That equals 0.7 times the probability of m. So if I solve this for probability of m, I get the probability of m is equal to 0.4 over 0.7, which is really just 4 sevenths. Tricky question. Okay, should have done these problems already. Don't wait for me. Use the formulas, figure out what's being asked. Suppose that 62% of graduates from your high school go on to a 4-year college. 15% go to a 2-year college. 18, so I need to figure this out. 0.62 4 years. 0.15 2 years. 0.18 military. And the remaining, I don't even know what the remaining are, so let's get the calculator out. 1 minus 0.62 minus 0.15 minus 0.18 equals 5%. So 0.05, what do? They go to work. They go to the workforce. If a randomly selected student is not going on to a 4-year college, what is the probability that he or she will join the military? So this is the probability that they're going to join the military given they are not going to a 4-year college. So what is everybody, so really my new thing is I got to get rid of 4-year colleges. Get rid of those. So what is the probability that they're going to join the military given that they're not going to, well, how many people are there? There are 38%. So that would be equal to, now my new domain is 38%, and how many are going to the military? 0.18. So 18 over 38. Oops, that's not what I want. 0.18 divided by 0.38. 47.3. Must have been 0.3 something. That one was a little weird. Given two events D and E such that probability of D is equal to that, probability of E is equal to that, probability of D or E is equal to that, what are we going to do? Independent and mutually exclusive. Independent but not mutually exclusive. They really don't have anything to do with each other, but we'll see. Let's see. So really we're just talking about whether or not things are independent or mutually exclusive. So let's address mutually exclusive. Mutually exclusive says that the probability of D and E is equal to 0. Or in other words, that the probability of D or E is equal to the probability of D plus the probability of E minus the probability of D and E, but since this is 0, we don't have to worry about it. So what is the probability of D or E? 0.637 equals, what's the probability of D? 0.340 plus the probability of E, 0.450, and that's 0.637 does not equal 0.790. So they are not mutually exclusive. Gone. I don't know, but that's the only thing I can get rid of right now. I don't know about the rest of that. Oh, neither, well, I don't know, that's the only one I can get rid of. Oh, wait, this one says they're mutually exclusive. I can get rid of A and C. All right, so now I got to check for independence. Now, check for independence is the probability of D is equal to the probability of D given E. That doesn't really help out. Oh, wait. Actually, in this case, what we're going to want to use is, because we're going to use the same formula, we want to use that probability of D and E is equal to the probability of D times the probability of E. So we're going to see if they're independent or not by using that. So let's see. We'll use the same formula. Probability of D or E is equal to the probability of D plus the probability of E minus the probability of D times the probability of E. Now, if they're independent, this should be true. If they are, in fact, independent, this should be true. Well, we know this to be 0.637. We already added those up to get 0.790. We just got to subtract off, let's say this is 0.34 times 0.45. That's not what I want. Why do I keep touching that? So 0.34 times 0.45. 1.53 minus 0.153. So is 6.637 equal to 0.790 minus 0.637? So they are, in fact, independent, but they're not mutually exclusive. So we're on to 819. Let's fill these in. Oh, so let's assume I assume by now you filled these in. This should be 0.13. This should be 0.1. This should be 1, and this should be 0.46. So what is the probability of B? What is B? AP courses, 0.43. What is the probability? I mean, I can put over 1, but it's still 0.43. Probability of E, a senior, 0.54. Probability of A and E, IB and senior. IB and senior is right here, 0.13. What is the probability of A and B? Probability of A and B. There it is. Those are nothing. There's no correspondence. All right, what is the probability of B given D? So given that they're a junior, so now junior is my new denominator, 0.46. So what is the probability that they like B, which is AP, given that they are juniors? That would be 0.12. 0.12 over 0.46, which, if you do the math, is 0.261. What is the probability that E, given that they're A? Now, A means my new universe is this, so my denominator is going to be 0.41, and now I want the probability of E, which is senior, 0.13, which is 0.37. 0.317. 0.317. Am I done? C or D. Remember, this is, we're going to have to get rid of the highlighted, the overlapping stuff. So let me overlap. What was it? C or D. C is no preference. And D is junior. So we're going to do 0.46 plus 0.14. Excuse me. We're going to do 0.46 plus 0.16, right? Minus the part where it's overlapping. Where is it overlapping? 0.06. And we should end up with 0.56. And E or A. Let's do E or A. Oops, that should be a 1. So E or A. What's E? Senior. Or A, IB. So we're going to add those up. 0.41 plus 0.54. 0.54 plus 0.41. But we need the overlap. What's the overlap? Oh, the overlap is 0.13. Oops. A or E. Ooh, I have the wrong answer there. I subtracted off 0.28, but A, let me make sure. Let me delete these again. A is IB courses, or E, which is senior. So the overlap is 0.13. So I should have been subtracting 0.13. So 54 and 40, that's 95.82. All right. Are A and E independent? In other words, we have to make a test. Does the probability of A equal the probability of A given E? Another mistake. You know, and I keep doing this one. If you want to, you can also do this one. I think this one might actually be easier for you because I think we've already done it, A and E. We've already done it. So is the probability of A and E equal to the probability of A times the probability of E? This is another very simple test. Well, the probability of A and E I've already done. That's 0.13. Does that equal the probability of A, which we've already done, 0.41, times the probability of E? If you look up there, it's 0.54. Well, this gives you 0.13 does not equal 0.2214, therefore not independent. Are B and D mutually exclusive? In other words, does the probability of B and D equal 0? So let's see what the probability of B and D is. The probability of B and the probability of D is 0.12. Since the probability of B and D equals 0.12, they are not mutually exclusive. You would write that out. Don't be lazy. All right, let's do a few more. There is one very challenging problem. I'm going to do it, but I'd love to know if you actually got it on. All right, since they did not tell us whether or not these were independent or not, I know that the probability of junk, J and K, is equal to the probability of K times the probability of J given K. This is a straightforward problem, shouldn't be a problem. 0.58 times 0.32, which is equal to another mistake. Not a mistake in math, just, well, I should check my math here. Here we go again. So 0.58 times 0.58 times 0.32. 1856, yeah, that's what I got. So 1856. 0.8156, there it is. If the probability of F equals 0.26 and the probability of U is equal to 0.71 and the probability of F and U equals 0.52, are events F and U independent? I know some of you want to use a few of those letters in this problem, but that's okay. We want to check for independence. So that means that the probability of F and U has to equal the probability of F times the probability of U. In other words, 0.52 has to equal 0.26 times 0.71. We just want to test that quick test for independence. So we go to our calculator and we do, what is it? 0.26 times 0.71, and we get 1846. That's really weird. So 0.52 does not equal 0.1846. Therefore, they are not independent. All right. Ooh, what's this? If the probability of f equals 0.3, the probability of not f equals 0.57. Uh-oh. The probability of h given f is equal to 0.25, and the probability of h given not f equals 0.62. What is probability of f and h? All right, so the probability of f and h is equal to the probability of f times the probability of h given f. Do I have that information? Yes. So this is equal to probability I have some weird stuff written in there. I got a mistake written in that one too. Man, this is like a mistake-ridden problem. Because I'm not given probability h, so this is equal to the probability of f, which is 0.43, times the probability of h given f, which is 0.25. And this is equal to 1/4 of that, which is 0.1075. Yeah, 1075. What is the probability of not f and h? So the probability of, in other words, f complement and h is equal to the probability of not f, f complement, times the probability of h given f complement. I'm just writing it smaller so I can get in here. So the probability of f complement, or not f, and h is equal to the probability of not f, which is 0.57, times the probability of h not f, which is 0.62, which is equal to 0.3534. What is the probability of h? Well, the probability of h is equal to the probability of all right, so, sorry, I took a break. Dog issues. So probability of h is equal to the probability, believe it or not, it's equal to the probability of f and h. Oops, I put p. Probability of, oh, why did I switch pens? Probability of f and h plus the probability of not f and h. Now this one is kind of difficult. This one is really hard to understand. This is going to be 1.075 plus 0.3534. So the final answer here is 0.4069. And that's really because the two events are mutually exclusive. So this is really the only way this can happen. But most kids don't understand that. But if I go to a two-way table, you might be able to understand it if I went to a two-way table. So let's say I said this was f, and dog issues, f and f complement, h and h complement. Well, I came over here and I said the probability of f and h is 0.10575. The probability of not f and h was 0.3534. Well, isn't right here the probability of h? Like if I was doing a two-way table, these two things right here would add up. Remember, this is my h column. This will be add up to the probability of h. And that's because if I put h with all the things that are f, and I put h with all the things that are not f, then what's left over is just the things that probability of h. So hopefully you understand that. If not, that's a tricky question. I would never put one that difficult on a test. The mathematics of the Clark Institute went back in time machine designed by famous Dr. Clark. What they discovered was that the probability of a plague was 0.39. So the probability of the plague was 0.39. The probability of famine was 0.52. And the probability that both plague and famine was 0.15. What is the probability of famine given that there is a plague? So what is the probability of famine given that there was a plague? Now, are they independent? We're not told that they're independent. So we know if we're not told that they're independent, we got to say that the probability of plague and famine is equal to the probability of plague times the probability of famine given plague. Correct? What am I looking for? What is the probability that there's a famine given plague? So I know that this is 0.15. And I know that's equal to the plague, which is 0.39 times the probability of famine given plague. So I just divide by 0.39. And I get the probability of famine given plague is equal to 0.3846. All right, the Lasky Fashion Magazine. We're happy to have the founder that was both a fashion-forward and a fashion-forward math person that's math savvy. Miss Lasky uses her math skills to drive the articles in her magazine. She discovered that the probability that the stock market declines, so the probability of a decline, discovered that the probability of the stock market declines is 0.4. The probability that skirts will lengthen is 0.5. So probability of lengthening is 0.35. And the probability that both of her events happen at the same time, probability that the stock market declines and we lengthen the skirts, is 0.3. Are the two events independent of each other? So if they are independent, then the probability of decline and lengthen has to equal the probability of decline times the probability of lengthen, if they are independent. So we know this to be 0.3. Is that equal to 0.4 times 0.35? That's our test. And this is 0.3 does not equal 0.14. Therefore, they are not independent. The following is a table of smokers and their mortality rate. Answer the following question based on the table. What is the, these are kind of tricky. What is the probability that a 20-year-old will survive to 60? What is the probability that so we're starting out with 20,000 people, but that's not what I asked about. What I asked about is what is the probability that a 20-year-old will survive to 60? So if they're 20, so what is the probability they get to 60 given that they're already 20, basically? So how many are at 20? Well, at 20, I've got 19,400. How many survive to 60? 12,200. That's your probability. And if you wanted the decimal, it would be 0.26289. What is the probability 60-year-old? So 60-year-olds now are my new universe, will survive to be 80. Well, how many of them get to be 80? Oh, of the 12,200, only 2,600 make it to 80, or 0.2131, 21%. Tough question. All right, here we go. Here's the beast of them all. So if you are able to do this problem, you are manning up and ladying up and doing crazy. This is a tough question. The latest statistics in the U.S. population in the United States taking AP statistics exam. Scoring a 4 or 5 would be 40%. Scoring a 3 or better, or 3 would be 20%. And scoring a 1 or 2 would be 40%. Of the people who scored a 4 or 5, 90% received college credit for statistics. Of the people who scored a 3, 75% scored college credit. Of the people that scored a 1 or 2, only 3% received college credit. If a person received college credit, what is the probability that that person scored a 4 or 5? So I think what we finally need to answer is, well, I need to define my events. Let's define my events. Let's define them up here. Let's say A is the event of scoring a 4 or 5. Let's say B is the idea that I scored of 3. C is score a 1 or a 2. D equals got into college. No, got college credit. College credit. E is no college credit. All right, you got that? Now, try it on your own. See if you come up with it. Play around with it. Because, I'll tell you what we're looking for in the end. What we're looking for in the end is if a person received college credit, so if they got D, given they got D, what is the probability they got a 4 or 5? So what is the probability of A given D? That's what we're looking for. Probability of A given D. Well, if you work your way backwards, that's my hint to you, work your way backwards and see if you can figure that out. Now, so pause it and see if you can. Are you back? All right, so what I'm going to do is I'm going to put all the stuff I know. The stuff I know is I don't know what that is. What do I know? That the probability of the people who scored a 5, so the probability I received college credit, given that I scored a 4 or 5, is equal to 0.97. The probability that wait. Whatever. The probability of the people who scored a 3, so the probability of people who scored a 3, got college credit is equal to 0.75. And the probability of getting college credit if I scored a 1 or 2 is equal to 0.03. What do I know? I'm thinking about I'm sorry, pause it for a second because I want to think about what hint to give you. I think I want to go back to this idea of what you need to find at the end. The probability of A given D, right? That's what we want to find. That's our ultimate goal. So if I knew the probability, if I remember correctly, the probability of A and D is equal to the probability of D times the probability of A given D. Correct? So if I just divide by the probability of D, I get what I'm looking for. I know I need to find the probability of A given D is equal to the probability of A and D over the probability of D. Okay? So that's what we have to find. So how do I find the probability of D? Well, the probability of D is really equal to the probability of A and D plus the probability of B and D plus the probability of C and D. If I add all those probabilities up, that's my total probability of getting into college. So my goal is now what I got to find is the probability of A and D. So the probability of A and D is equal to the probability of A times the probability of D given A. Now, I know the probability of A, it's up in the top, 40%, got a 4 or 5. So I know that it's 0.40. It might have been helpful to say, well, whatever. And then the probability of D given A is 0.97. Well, if I add that up, I get 0.388. Oh, I already have my numerator. Ooh, that's terrible. 0.388. All right, so now I got to go back, and I want to find the probability of B and D. So that's the probability of B times the probability of D given B. Well, the probability of B is 20% times 0.75. And that's equal to I never wrote 0.73. Oh, this should be 0.75. I think my numbers are off a little bit. Hold on. 0.2 times 0.75. 0.15. All right, I'm off a little bit on my answer key here. All right, and then I've got to do the probability of C and D, and that's equal to the probability of C times the probability of D given C, which is equal to, what's the probability of C? 40%? So 0.40 times 0.03, and that's equal to what? 0.012? 0.012. Well, if I add all those up, 0.012 plus 0.388, I get 0.55. So I get 0.55. So there's the numerator all over 0.55. So my answer is 0.705. Maybe a bonus. Maybe a bonus someday. That's it, kids. That's all she wrote. Oh my gosh, I'm so happy this is over. All right. We still have the practice test. We still have the actual test. We got a lot coming, kids. So keep paying attention. Keep working hard, all right? Get y'all on the flip side. Oh, press stop.